Westminster School of Architecture and Cities this evening. We're very excited to be joining you via this sort of online format. The title of our lecture is Research as Practice, Material Formations. There are certain concerns that drive our work, architectural, environmental, and technological. And they're all tied to questions of material and methods of making on the one hand, and form or formation on the other hand. We would like to unpack some of these concepts and their conceptual entanglements by showing the work of our office and our research at Cornell from the past few years. This work eventually all led to the creation of a small architectural prototype, the Ashen Cabin, which we will present more in detail in the second half of the talk. We believe the issues of making and forming are fundamental to how we operate as HANA. The various projects presented in this lecture seek to inform form through a variety of methods of production, synthesizing new material systems, tectonic articulations, environmental practices, technological affordances, and forms of construction. In the past few years, we created open source construction machines, which we argue inevitably affect how we think and design through making. In our work, we aim to mind the tension between machine means and architectural ends. And some of the work today will confirm what we think about how we can build and experiment. The following projects are work in progress and aim to give expression through design to some of these questions. We spent the last 5 years building infrastructure and framework for architectural explorations across scales, starting from the design of tools, moving to prototypes and installations, and then combining the research into the construction of a small building.
So starting with the tools, about 5 years ago, Leslie and I became interested in a new method of making, which was at that point concrete 3D printing. And at that time, we didn't have access to a robotic arm or more advanced fabrication technologies at Cornell. And we had to essentially develop our own tools to start this type of research. So in order to do this type of work, one needs the tools, one needs the advanced manufacturing capacities, and one needs the facilities, but what do you do when you don't have them? And so we had to become inventive, and we had to build our own machinery to do the type of research that we wanted to do. In this image, you see on the left a 3D printer that Leslie and I built in 2011, RepRap. And then on the right, you see the printer that RCL developed at Cornell in 2016, which is a scaled up version of the same machine. So this printer is fully open source. It runs off an Arduino board with slightly modified firmware. And for all of you who are interested, a 3D model, a parts list, and a wiring diagram can be downloaded on the RCL website. Now, we do think that fully unpacking the manufacturing tool or the machine is actually an exciting opportunity for architects to reclaim authorship over processes of construction, which we think fundamentally influence the way we can build and might also change the way we ought to build. And in some ways, we are facing a crisis of manufacturing and production. And the building industry, on the one hand, is incredibly unproductive. Construction techniques are changing, and we as architects can and must have agency in this process of transformation for various reasons. And so the tools are sort of a part of that conversation. So while this machine is only a framework, our architectural thesis is that with these new tools come new architectural opportunities. And this printer data list then gave us the flexibility to attempt to rethink construction through the lens of this new tool. And what's important to note is that we also believe that this new technology comes with a responsibility to make these tools broadly available. And so this printer itself costs about $6,000 to make. With the information that we know now, we can probably get this price down to $5,000, which is significantly lower than a comparable machine of the same size if you were to build it or buy it sort of from a manufacturer. And so this printer was developed and built over a 3-week period in a collaborative option studio at Cornell in 2016 called Villa Additiva. And here you see the printer in its first photo shoot. It's still all nice and sparkling clean. And then here you see it a couple of weeks later, all dusty and dirty, 3D printing concrete. And so after a period of material development and machine modification, this printer is now able to print full-scale building components in foam, in recycled plastic, and in concrete. And for us at HANA, this tool has opened the door to novel and perhaps unfamiliar architectural speculation. And I'll get to that in a second, because we, at some point, well, the year after we built the printer, we thought, okay, maybe this format is interesting. Can we also get a robotic arm? Because we didn't have access to a robotic arm at that time. And the RCL lab has very limited resources, and we still had to be inventive when it comes to equipment. And so as it turns out, you can go to eBay and you can purchase a used KUKA KR200-2 for $8,000. This is how it comes when you buy it. It's not free, but it's considerably cheaper than buying a new robotic arm. And the robot we purchased was formerly a welding robot for GM, and it produced cars in a plant in Louisiana. And while the machine itself is obviously proprietary, it was important for us to keep the rest of the project open source and accessible for anyone. So in terms of cost, it's actually hard to find a cheaper robot. This is a rough cost breakdown of the robot and the self-developed foundation system. As with the 3D printer, there's a certain amount of hacking that's required to make this robot work for architectural production. And all of the information for how to set up the printer and the robot is available, as I said, on the RCL website, but also in an Acadia paper written by the lab called Open Source Factory, which is available for download online for free. And so for us, these two tools, the robot and the 3D printer, enabled research that sort of pushes the boundaries of material and construction at HANA. And so now going back to the 3D printer and to 3D printing of concrete, our initial interest was in the following process. And this is one of the first 3D prints that we did with concrete that finally worked. This is like a 3-dimensional drawing. The machine horizontally deposits one line after another. And if those lines are then shifted through corbelling, the printer starts to create spatial form. And we think that inherent in this rather simple process is a complex architectural language of concrete 3D printing.
And through this process, we discovered that the 3D printer, a machine which has long been characterized as characterless because it can presumably print anything, is in fact exactly the opposite. It has plenty of characters, what we like to call productive constraints. Most of these constraints are informed by concrete rheology and gravity, which we call the two frenemies of concrete 3D printing. In the project Additive Architecture Elements, our research question is, what is the architecture of 3D printed concrete? How can materiality and the unique fabrication opportunities and constraints of the tool inform the design? It turns out that building the machine was perhaps the easy part, with the aim to derive an architecture that is intrinsic to the additive manufacturing process. We started by experimenting with dozens of initial concrete mixtures and printing failures to understand the material's tolerance and its urge for imprecision. And also when printing in concrete, the same rules apply as in a small desktop 3D printer. But gravity takes on an altogether different role in this process. Cantilevers have to be carefully constructed, new support material strategies have to be developed, and tool paths have to be carefully manipulated. And so you can see in this image, we end up using this sort of reusable gravel formwork method. So we will be, we pour the gravel in as we print to create temporary support. So we see this manipulation of the 3D printing rule sets as a tremendous opportunity. Concrete printing requires the development of an entirely new architectural language or strategy, which takes into account the limitations of the process as well as its performative advantage. And as mentioned earlier on, this project aims to review the 3D printer's idiosyncratic architectural tectonics and narratives. And so in this exercise, we chose prototypical motifs, the floor, column, door, window, wall, and ceiling, and began to develop strategies as to how the layering of concrete, this relentless three-dimensional drawing of extruded lines of material, and the act of corbelling can suggest strategies for building. In this first element here, mushroom column, it works with the constraints of the gravity by printing upside down. So the drawings on the left actually show the printing direction of the column, with horizontal striation resulting in structural assembly that can then seamlessly transition between the vertical and the horizontal. In the 3D printed structure, all common architectural motifs and building components must be rethought to fit the logic of layer construction. For example, a concrete printer cannot print in mid-air. Therefore, the otherwise simple task of creating a rectilinear window opening in a wall becomes a de facto impossibility. And so in this element, the corb window, rather than drastically altering the process, meaning we stopped the machine to insert a beam, we saw the shortcoming as an opportunity for design. And one logical consequence for the window is to cantilever incrementally and become a triangular corbelled arc. Suddenly, seemingly advanced technology relies on obsolete or archaic structural strategies such as corbelling. In the case for the element force column that you see here, the modification of printing direction, in this case we're printing in section, is deployed to overcome the shortcoming. Printed in section, the force column hints at the potential to deposit material where structurally necessary. And through this process, we're able to introduce then porosity in the elevation. There's also the smart poché wall, similar to the force column, explores the manipulation of concrete density to optimize for structural performance, and tests how the optimized structural performance might begin to be architecturally expressed in a wall assembly. The potential for excessive ornamentation is brought up in the element ornament. In the full-scale prototype, we were playing with a delamination of layers to create screen-like moments of transparency for this sort of portal. And ornamentation can also occur horizontally in the case of floornament. So besides the patterning, the floornament could be structurally and algorithmically optimized to accommodate varying floor loads. 3D printing also opens the possibility for an integration of building systems and furniture. The ceiling element that you see here is an expressive play on ducts for ventilation, reflectors for lighting, for it to become a type of performative poché for building systems. There are certainly multiple narratives at play in this project, and we chose to present the work with a particular speculative focus. We can also discuss the work in various other terms as well. From a technical point of view, there are multiple advantages to 3D printing. For example, all of the elements' geometries were constructed without the use of formwork. This constitutes a paradigm shift for concrete construction and allows for a radical mass customization of building and building components. There's also great potential for material savings because the 3D printer can deposit material where structurally necessary. It becomes an enormous advantage and paths towards smarter construction. However, there are severe shortcomings to working with concrete. The cementitious material itself has to change and become drastically more sustainable for 3D printing to become a viable future technology. So while our concrete projects explore the design benefits of 3D printing, we as designers have a responsibility to dig deeper and constantly challenge the material we work with. In the future, we hope and aim to be able to replace concrete with more sustainable alternatives. So following our initial test in full-scale 3D printing through building elements and components, we investigated how the additive architecture elements can be scaled up and deployed in the building context. The Fabricate Lilong project explores the potential of computational protocols such as additive manufacturing at the architectural scale as a speculative housing design. The elements explored earlier are examined in the context of housing structure. So the smart poché wall here is expanded in the context of a multi-unit housing. It can be densified for structural load, thickened to become a party wall, and attenuated to meet the thinness of glazing transitions. In the core window elements, it is explored here both as window and entrance opening at the housing scale. And the ceiling element can start to form individual modules or organized into a cross-modular system with mechanical connections across multiple units. When we looked at the force column, it has the potential to transform into an integrated wall and beam system, which acts both as structure and a screen. Looking at the planimetric design at the cluster scale, the smart poché walls can be mass customized to address different domestic functions and expanded into thickened cores for utilities or for circulation. And so in this plan, it shows the housing modules organized in two different types of cluster configurations. The 3D printed cluster modules can be organized into continuous row houses inspired by its original typology, the Lilong, creating an urban fabric that operates both in section and plan. Apart from the typological transformation, the original spine organization of the semi-linear public space is transformed into a weaving network of semi-public alleys and courtyard spaces. We think that designing with the experimental projects like the additive architectural elements at the housing scale can offer alternate inspirations to build our city fabric, and perhaps offer solutions to address the crisis on housing and housing construction. This research is currently ongoing in our office, and our long-term goal is to make housing more customizable, spatially diverse, and economically accessible.
So it's very important for us that we test our ideas across scales, and we are actually quite interested to see how certain intellectual frameworks change and transform when translating from one scale to the other. And so the idea of robotic mass customization inspired our Rolling Stones project, which we did in 2018 and was the winning design for the Folly Function competition sponsored by the Architectural League of New York and Socrates Sculpture Park. And the design itself is deeply informed by a program, and in this case, it's public seating. The competition brief did call for a design that could be movable by visitors and staff, but is also solid enough that visitors are discouraged from removing it from the park itself. And so concrete gravity works in our favor this time around, and these pieces are sort of difficult to move. At the same time, movement is really a critical part of the project itself. As you can see in this image here, the idea is that these pieces can be moved through the park by rolling them sort of around their axis. And each roll also produces a different seating configuration for the person who wants to use the chair. So this project, leveraging movement architecturally and as a folly itself, the playful design does encourage this creative interaction between user and furniture, and does allow park visitors to discover a variety of seating configurations while moving the seats across the lawn. So responding to scales within the public park landscape, the Rolling Stones can form either a long and continuous bench object, or they can aggregate into smaller benches, or like in this image, disperse entirely to form different size seating groups or solitary compositions. So each seat is different in scale, color, and geometry. And the act of rolling adds additional complexity because it does allow for the variety of chair configurations. And some of these chair configurations encourage a more upright seating position, while others animate lounging and relaxation. So, and in this project, 3D printing with concrete enables the creation of 25 affordable and self-similar, but ultimately entirely individual seats. So we're no longer bound to the relentless paradigm of standardization. And 3D printing opens the possibility for this type of design freedom, customization, and individuality. So even though this looks like a cookie cutter, it's not a cookie cutter project. Well, the sectional profiles reference archetypes of chairs, seats, and lounge chairs. The layered fabrication process itself does also create a comfortable textured seating surface. The material that we used in this 3D printing process is a Portland cement-based mortar, which is then reinforced with nylon fibers and results in a strong concrete assembly. And in addition, each seat is supported by 3 steel rebar profiles that you can see here in the left drawing. You can see one of these layers. The steel rebar is then embedded within a double concrete layer. And Leslie hinted at this in an earlier slide. For us to enable the creation of these more extremely cantilevered forms, the seat's interior are actually supported with a bed of gravel during printing. And this layer of gravel remains imprinted on each of the chair's interior surfaces and giving it this sort of geologic character, which is also an honest reading of the fabrication process itself. So this video shows the making of the Rolling Stones. Here are a couple of photos of our early prototypes that we submitted for the competition entry itself. And the idea of them forming a long continuous object that transforms, or different configurations in the park itself. So the printing process is both simple and complex. Here you see the first layer being put down onto a sheet of plastic. The first layer is critical for stability, and you see that the printing itself is not as automated as one might think. It's a dance between humans and machines to get the project working. We had to test a number of rebar options for this project because obviously concrete is very good in taking compressive forces, but not very good in taking tensile forces. And ultimately, we settled on a hefty piece of number 4 rebar that is custom shaped to the profile of the Rolling Stones, welded at the edges, and then inserted 3 times to provide stability for the project itself. So here you see the printing process. It takes about a whole day to 3D print one batch of the Rolling Stones. And then they cure for about 2 days, and then we excavate them. And this is an initial load test that we did.
It could go heavier, but that's how much weight that we can physically lift onto this seat.
Yes, and the Rolling Stones are now on view at the Art Omai Park in upstate New York. If anyone is doing a trip to the US, please feel free to stop by. Now, besides exploring the architectural potential of horizontal layer printing, or let's say conventional printing, we're also interested in developing new processes of manufacturing. And so this sub-additive 3D printing project was done at RCL with Christopher Battaglia and Martin Miller. and it explores technological opportunities to conserve material resources. And so, so at RCL, based on Chris Battaglia's thesis, we developed a spatial method of concrete 3D printing, where the concrete gets deposited on a support material, in this case gravel, that is previously shaped by the machine. So you're printing spatially as opposed to horizontally and creating form through corbelling. So depositing cementitious material on a supportive aggregate is not a new thing. For example, the Philips Pavilion at the Brussels Expo in '58 was one of the first modern examples to panelize a large complex surface through landforming. And so they were casting on a shaped hyperbolic sand form, and then multiple panels were produced as sections on the surface, transferred to the site, and then post-tensioned to create the structure. This process is a bit different. But here's what's smart about this technique. So the same machine that prints the concrete is then used to create the flexible gravel formwork. And so in the first step, the printer creates a surface that matches the curvature of the thin shell geometry, so making its own formwork essentially. And then in a second step, the concrete material is deposited on the reusable gravel formwork. And so with this method, one can rapidly print highly mass customized and optimized gridded thin shell structures. And here you see the same printing process using a robot. It's still a bit messy, and we have to increase accuracy. So using the 3D printer's flexibility, we can use formwork or form finding methods and structural optimization to determine the lattice density required at each point within the surface. And then depending on the structure, we get different lattice patterns, which also reduces waste material. So in our research in the lab and in the practice, we think that it's paramount to test full-scale prototypes. And so what you see here is a mock-up of one of these sub-additive printed arches, weighs about 150 kilos and was printed in the span of 1 hour and can be rolled up for easy assembly. And so as a new method, this sub-additive 3D printing leverages digital workflows to then produce structurally, materially, and spatially optimized building components, while also dramatically reducing waste material. Now shifting the focus from concrete towards wood, the Lognaut project is one that emerged from our first initial exploration with custom-based tools for the robot. This was also born out of an option studio, and it's part of a research lab project. And as a building material, we do encounter wood in the shape of 2x4s or plywood or other standardized materials. But the diagram on the upper left shows that wood comes from trees that are usually non-standard. So the Lognaut is a method for creating complex timber curvature by cutting and reassembling tree trunks. It's a rather simple idea. So one can cut and reconstitute a log in order to bend it spatially. And these early studies show how the Lognaut creates an infinite loop of round wood curving three-dimensionally along its length. And this is an image of an early prototype that elaborates on the idea of curvature generation and also incorporates a small number of tree forks and highly irregular wood geometries. So once assembled, the wooden components then do form the spatially complex figure 8 knot. And in a reciprocal design process, the project really aims to foster synergies and feedback between material, fabrication, digital form, and full-scale construction. Here you see a view from the top that shows the completed project, and you can sort of see the figure 8 knot. And there are a few technical things worth highlighting in the project. So Lognaut does use computation to optimize each joint for moment forces. And additionally, each of these joints are precisely rotated to resist local torsion. So we used structural optimization solvers, simple ones as Caramba, to analyze the forces in each segment. And then this information was fed into the design of a series of physical prototypes, which you can see here. And we tested a number of conventional finger joints, mortise and tenon joints, dovetail joints, as well as custom steel dowel joints. And each of these methods did exhibit severe shortcomings in either structural capacity, ease of assembly, or ease of robotic fabrication, which is why we settled on this final joint, which is a custom trifold mortise and tenon joint, which is self-supportive during assembly and also able to resist bending in multiple directions. And so the project was designed for disassembly, which is why we used lag bolts for connections. This is also a fully permitted project, so it had to undergo structural reviews at the university level. And one of the requirements was that we use the steel. I believe that we could have done this project without steel bolts. And so to optimize load behavior, the radius of the round wood does reduce towards the apexes, meaning at the top, and the knot thickens at the ground level where moment forces and loads are the highest, as you can see sort of in this fly-through video. This is an image of an early prototype where we tested for accuracy. And in the next slide, you can see the fabrication process and how it plays out. So we are first squaring off the log, cutting the end, and sorry, my slide just moved. I hope you can see the video. And so once the angled surface is created, the mortise and tenon rough pass is cut at approximately 4 inches deep. Next slide. And as a next step, the finishing cut is executed where we use the side of the bit instead of its tip, and thus further taking advantage of the robot's 6-axis flexibility. So this is an overview of the entire process. And this is the milled pieces waiting to be assembled. And then, as with all of our projects working with small budgets, we did not have access to heavy machinery and therefore had to develop a self-sufficient construction method that requires only minimal formwork and support. So the log knot was assembled by our team over the course of 3 days. Each component is lifted in place by hand and then fastened in place using the geometry of the joint to guide the form for the arch itself. And so after each completed arch segment, the structure is attached to the ground using earth anchors. And so in this next slide, in the drone shot, you can see at the top emerging that during construction, all that's needed is a minimum support of attached 2x4s. You can see them at the very top holding up a portion of that arch. And so to conclude this project, unfamiliar notions of craftsmanship and precision, both digital and analog, emerge from log knot's conceptual design practice and characteristic construction technique. Log knot was exhibited as part of Cornell's 2018 biennial called Duration, Passage, Persistent Survival, and does address the theme on multiple levels. Environmental cycles, birth, growth, and decay are intrinsic to complex forest ecosystems and processes. And conceptually and spatially, the log knot project references these eternal cycles and reciprocal relationships between systems, both natural and technical. The infinitely looping structure is an interplay between archaic natural geometry, advanced computation, and state-of-the-art digital fabrication. And by questioning how forests are used as a resource, log knot provides a critical commentary on various perpetual wood cycles, economic, environmental, and cultural in nature.
The last project which we want to show today is perhaps a culmination of all the separate research agendas that we showed you in this lecture so far. Ashen Cabin is a project that started in the summer of 2017 and was finished in the summer of 2019. Informed by two material narratives, it is a small building made of 3D printed concrete and robotically fabricated timber envelope. In this first material system, Ashen Cabin explored how the horizontal layering of concrete and the active corbelling can suggest new strategies for building. The concrete structure is printed in components that function as sacrificial zero-waste formwork for the main structure. And then the formwork is printed in small sectional modules to be transported and assembled manually at the remote construction site. We developed a hybrid construction system with 3D printed formwork and cast-in-place concrete with custom rebar. As you can see in this top-down video, this drone video here, each leg is then filled with foam in the void in the center of the legs, and concrete is poured in between to form the structure. Here's a photo that you can see the assembly of the chimney going up, and essentially you can see it's printed in smaller sectional modules. The slabs are organized in 9-square grid, reflecting the interlocking patterns of the legs beneath. And in this hybrid building process, tectonic expression is generated by fabrication method and its materiality. For example, in this photo, the G code and the print path becomes visible as the ornamental pattern of the 3D printed floor slabs, bringing back the notions of floornament from our additive architectural element. Corbelling is also achieved here through sectional transformation and becomes an expressive and functional motif, allowing horizontal layers to seamlessly transition from the leg to the slab and then into the chimney above. The resulting concrete structure lifts off the ground and is characterized by 3 programmatic areas: a table, a storage seat element, and a 7 feet tall fireplace. Sorry, a 7 meter tall fireplace. We use feet in the US. So big difference there. In the second material system, the Ashen Cabin is informed by a key environmental crisis of the ash trees in North America. The emmer ash borer is a small beetle whose larvae hatch underneath the tree's bark and cut off vital layers that transport nutrients within its trunk. This invasive EAB threatens to eradicate most of the 8.7 billion ash trees in North America and has drastically transformed entire forest ecosystems in the process. As of October 2018, it has been found in 35 states and several Canadian provinces. And as a reference, almost every 10th tree is an ash tree. While we as designers cannot help the dying trees, we believe that the infested trees form an enormous and untapped material resource for sustainable wood construction. Due to their irregular geometries, many of these infested ash trees cannot be processed by regular sawmills and are regarded as unsuitable for construction. So in this project, challenging preconceived notions about material standards in wood similar to the log knot, Ashen Cabin utilizes infested trees for its envelope, which unfortunately are widely considered as waste or simply used as firewood. We developed a process that involves 3D scanning and our custom robotic platform to transform irregularly shaped waste wood into an abundantly available, affordable, and in a way morbidly sustainable building material for the Anthropocene. With this method, we can slice irregular tree logs into naturally curved boards and strategically assemble the boards to form different surface conditions. Ironically, in order to advance environmental resiliency through architecture, we used resources that themselves were not resilient enough. And so in the process of slicing the wood, we could adjust the thickness of each cut. And therefore, then the robotic cardboards can be assembled into single curvature or double curvature surfaces, as you see in this diagram here. The original log and then the type of board and its superficial or formal condition that we can achieve. To process and design with the logs, geometric and form finding assembly protocols from form to log and log to form were developed for this project. The custom protocols and scripts enable the design team to easily toggle between design concepts, material reality, and fabrication constraints. So this drawing shows one of the facades in the cabin, and then the scan logs that were used to construct each of the panels. And here's a kind of conceptual drawing showing the initial conceived form and its relation to the natural log, whether they're forked, straight, or curved members. In this image here, you can see that the logs are sliced according to their natural curvature, but the thickness could be varied. So we use these slide boards to array them into interlocking SIP facade panels. And the solid offcuts can be structurally integrated into the assembly, which results in a minimal waste fabrication method. On the drawings, the Exxon drawings on the left, it shows the SIP, the insulated panel facade with the exterior curb board and then foam insulation sandwich in between, and then a layer of inner ash boards. The facade assembly is fully ventilated, detailed to manage shrinkage, and does not require an additional ring screen.
So before we continue to show the completed project and conclude the lecture, we also wanted to take a moment to talk about our own personal crisis of production and automation that we reflect upon frequently when building our own projects. So we usually do present the Ashen Cabin through a front of house type of narrative only, where we highlight inventions or in timber or concrete construction. But I thought it might be useful for this lecture to include a small visual essay of missed opportunities, shortcuts, compromises, failures, and some successes that offer further food for thought and discussion. And this focuses mainly on construction. And so in the process of translating robotic fabrication methods in practice to a building, the back of house does reveal the inherent massive labor, workflows, and new complexities. So these images do serve as a humble reminder of how strangely anachronistic the construction of many buildings still is, and perhaps less anachronistic than what we're showing here. But for example, in this little structure, shovels, small rental equipments, and robots, in fact, must work hand in hand, and people to get the building built. And as we mentioned before, printers and people also work hand in hand in this delicately efficient dance between the machine and its operators, where we carefully balance concrete rheology, print extrusion times, and gravel reinforcement. And then, of course, while concrete parts can be mass customized with relative ease, the subsequent fabrication of rebar cages also increases in complexity, which then requires a substantial amount of time to fabricate and to customize. And then, of course, concrete doesn't transport itself just yet either. We had to build this project offsite in smaller components and bring it on-site because there was no infrastructure to put the printer on the site itself. And as I said, concrete does not assemble itself on the remote construction site. And so you see here parts of the assembly protocols or assembly methods. And as a result, for example, supporting formwork must be made for the concrete formwork to enable the cantilevers and other volumetric idiosyncrasies in concrete that we were after. And the emergence of a design idea, so for example, the cutting of irregular logs with a bandsaw robot, which we explored in these initial little study models, is only one aspect of this entire project. And one of the primary contributions of this project, we think, is not necessarily only the fabrication complexity from tree to board to panel, but also rather an investigation in how to translate these fabrication concepts into full-scale buildings from the ground up with all their architectural requirements, which is quite different from a project like the log knot, for example. This involves coordinating off-site fabrication sequences and logistics, and on-site construction logistics as well. And the Ashen Cabin itself was designed, fabricated, and built in 2 summers, one in 2017, one in 2019, for a total of about 6 months, also on a shoestring budget. And over such short time frames, the ambitions inevitably have to scale down to meet some of the deadlines. And our SIP envelope, for example, had to be deconstructed into a prefabricated exterior skin, which was then spray foamed on site to create this fully ventilated, but also experimental building envelope that leaks only a little bit. And at times we found ourselves enjoying this process of negotiating between digital fabrication, detailing, and design across technologies and material systems. So certain disciplinary problems, questions of joinery, material connections, proportion, performance, also began to reinfuse our discussions. And because the Ashen Cabin is a little building with many constraints and not a prototype or a spatial pavilion, it has to find these sometimes awkward compromises between conceptual ambition, material reality, economic reality, and schedule, which then resulted in this sort of mix of architectural means and construction methods. And the end result of these constant negotiations is this unfamiliar hybrid between digital and anachronistic processes of construction. And so returning to the front of house and to summarize the project, I'll hand it over back to Leslie.
We think that architecturally, Ashen Cabin walks the fine line between familiar and unfamiliar, between technologically advanced and formally elemental. And the undulating wood surface is strategically deployed to highlight moments of architectural importance, such as windows, entrances, roofs, drain scupper, or canopies. On the inside, we use our predominantly straight ash tree sections to create a contrast between the exterior and interior. The various window frames frames the views into the landscape or back into the building. So no longer bound to the paradigm of timber standardization, such as a 2x4, this project revisits woodcraft and design based on organic, found, and living materials. While transformed, the natural tree remains legible in the design. And in this photo here actually shows the door, and we often use the door as a perfect example to illustrate the sort of feedback loop, the back and forth between the design intent and then the raw material that informed the design as well. So the door handle, or this exaggerated door handle, essentially was derived from the curvature of this lock that we found. And here you see this exaggerated drain scuppers. And so in these photos that we share, the cabin combines a variety of fabrication methods, material applications, geometries, and types of construction. We believe that using newly inventive forms of making from the ground up at the scale of a building affords unfamiliar and exciting design opportunities. And at various scales, the cabin's performance, structure, and architectural expression are inherently derived from its digital construction protocols, robotic routines, waste materiality, and design logics. At the same time, in a mix of means, the project is inspired by top-down considerations such as precedent, building requirements, program, personal obsessions, and the creative misuse of technology. Together, the various and sometimes conflicting means, robotic, ecological, or otherwise, create the formwork and inform the architectural expression of the cabin. So we hope this talk conveyed that some of our work is a vehicle to address the various consideration that we have regarding materials and tools, and how we as designer can, through research and practice, begin to engage some of these ecological crises of materiality and invasive species. And lastly, we would also like to thank you and our team. In our final slide, we want to emphasize that our projects are team efforts, and we wholeheartedly thank our amazing, dedicated community here with our team and students, and project sponsors and Cornell University for their extraordinary support. And thank you for joining us tonight.
Thank you very much. Thank you so much. That was a wonderful talk. I think we have some questions. Oh, thank you, Pete. Pete, do you have a question?
Oh, no, don't put me on the spot. Can you hear me?
Yes. Yes.
Jolly good. That was very, very, very beautiful house. Excuse me. Interestingly, I would say you described it. I would say not designed, but the product of a process, which makes it really particularly interesting, especially when you said earlier on that you're kind of bringing authorship back through machines, which I thought was very interesting. So, you know, thank you for that. It really is a very beautiful house. I'm sure that everyone that's there who's seen it for the first time will appreciate it and appreciate how it is the product of your process thinking. So that's not a question. That's just a supportive statement, if you like. The question I do have, and I said right at the beginning, and I'm always confused about this in terms of the using concrete in construction, is that with my engineering hat on, it's a material that works fine in pure compression, but you need to reinforce it with some kind of tensile, you know, in your country you call them rebars, we call them steel reinforcement, but you need some tensile strength. Presumably the printer can't do that. So is all the concrete that you use working in pure compression, if that makes sense?
Mm-hmm. Yeah, I think that's a very important question in the context of concrete 3D printing. And you're absolutely right. The concrete that we print is unreinforced mainly. So for the Ashen Cabin, for example, what you see on the outside, the 3D print, is essentially a layer of sacrificial formwork, and then in there is the rebar and additional concrete that holds the whole thing up. You are right, though, that, for example, if one were to advance research, as has been done, for example, by the Block Research Group recently at their installation at the Venice Biennale, that little bridge that they built, which is a pure compression structure, which doesn't require the rebar. That's one way of doing it. If tensile forces occur, then one could think of a hybrid construction system where the concrete is a formwork essentially. But we're also working on other methods of reinforcement to try to integrate reinforcement into the printing process. But it's a tricky thing because it depends on scale, it depends on load, it depends on so many different factors. And so right now, most of the 3D printed houses that you see are hybrids, essentially, where the 3D printed concrete is essentially used as formwork and then partially as load-bearing structure when it only operates in compression.
Yeah, no, I appreciate you saying that, because I think it's often not clear in the media and in education, and when I'm trying to talk to students to understand this printing process, that is not clear, that it is actually, as you say, there isn't an inherent tensile strength in the concrete, and it's being used mainly as you describe it, as well, shuttering in a way, but in as formwork, if you like. So I think it's important. I just think it's important. I don't think it detracts in any way from what you've achieved, but I think it's important that it's stated clearly as part of the process. Just because the whole history of engineering, many engineers say that the biggest changes in engineering were when we could start to give materials tensile strength after the Industrial Revolution, if you like. So I just think it's kind of important to state that. But as I say, it doesn't detract at all from the work that you've done.
Yeah, thank you very much for your kind words and for the question.
I think. Oh, here we go. We have a question here for online question. Oh, wait a minute. When? Oh, there we go. Adrian, are you there? Adrian says, as per your research and materials with the process robot materials, should this become produced at mass for? Oh, I am, but fortunately, here. This should become produced at mass for the architectural industries, particularly within buildings. What, in your opinion, will be the ecological effects of incorporating, I suppose, your process?
Yeah. Yeah, I think we'll use the Ashen Cabin as an example. I think we think in the sort of techniques can often be hybridized or learn from also existing building conventions. So, for example, the slicing of the log. The slicing of the log itself doesn't produce the architecture. It was actually finding a way to apply it or transform it into a building envelope. And in that case, taking the logic of a SIP, a structural insulated panel, which is a conventional building product, and using that logic to develop or integrate this rather unique process of making. And we find oftentimes is at the intersection of these type of hybridization, how we might be able to learn, but also adapt both these ways of customizing or using material differently with certain standard practices. It's kind of the intersection of something that's quite interesting. And they became opportunities potentially that we can start to mass produce or integrate into the building industry in that sense.
And maybe to add to this, I mean, I think it's a very important question, and maybe we need to subdivide it into materials. Mm-hmm. In the context of wood, I would say yes, definitely. I think as many people as possible should try to use emerald ash borer infested wood for construction, as CLT panels, as SIP facade, as glulam, and I think some of that research is ongoing because there are so many trees that are dying and that could be utilized in construction. With the concrete, the question is a bit more complex. I think anything concrete related, we could have probably a 2-hour discussion about the usefulness of concrete or the appropriateness of still using it. Our interest is, I guess, both in the material as much as it is in the process. And so we think, on the one hand, if you were to look at the project that we showed as purely interested by or driven by a fabrication process, then we do think that there are tremendous opportunities in 3D printing itself, and that process needs to be studied from an architectural point of view. Now, what the exact composition of the material is, I think that's something where we need to collaborate with engineers, where we need to collaborate with industry partners to try to find, on the one hand, better uses for the concrete. So, for example, using less material or using it purely in compression and trying to minimize it as much as possible. And on the other hand, trying to develop a printing ink, if you will, that is much more sustainable in itself, that maybe eliminates a large part of the Portland cement, that eliminates then also CO2 emissions associated with it. For example, Ron Rael and Virginia Sanfratello have now 3D printed larger buildings in mud, as has been done in Italy as well. And so there are other possibilities for 3D printing or the use of other materials in this context, which we think are pretty important. And so with concrete, maybe it's a yes, but, or it's maybe a bigger but than a yes, but the printing itself, we think, is a really relevant technique. That was too long.
Thanks. No, thanks. No, I mean, I'm gonna ask this, see if anyone in the room's got questions. No, thanks very much. But yeah, I wondered about clay. Is that something you have to fire it afterwards, so it's a version of the earth thing. But I mean, there are people doing 3D stuff in clay, and the clay would then lend itself to other other things, properties, evaporative cooling, I don't know, all sorts of other stuff, difficult to reinforce, and then you've got to fire it, I don't know, but yeah, I don't know, it just seems like no one ecologically is, you might correct me here, but not in this country. There's a lot of clay in the UK, and no one has said that we shouldn't be using clay at the moment, but I mean, maybe that's next. The other thing I just wanted to, thanks so much for I think the timber thing, super interesting in a way, because you had to work with such difficult or complex curved timber with the ash dieback stuff, that in a way you've learned a whole kind of complex process that you could apply to kind of more regular, let's say, standardized cutting of other regular timber or not diseased timber, but thicken and thin it in different places. So you could bend it, or it could be struck, so that in itself seems to be really super useful. So I just want to thank you for the back of house stuff is much appreciated. So it's really nice to know you get not the spin of a project, you get the good side of a project. It's nice to know the reality of doing something over couple of years. Other questions in the room, because we have a roving microphone here. So
any questions?
Here we go.
I have a mic here.
I'm going to try this. See how it's
going.
Switch over.
Hi there. I've got a question in regards to maybe how you organize the projects within the university. I don't know. I guess you have a research unit, or how do you get the manpower to develop these, but also to build?
Yeah. So within the university, we each have our own research lab, and where we develop some of the, let's say, initial material investigation, or in this case, with RCL, the building of the tools, and it is in the practice that we translate some of these methods into architecture. And one example we like to give is, let's say, slicing of the log. The slicing of the log itself does not give us a building or translate into envelope system and structure system in that sense. And so this is where we think research and informing practice, and also practice informing research, becomes very, really relevant in what we do. How we can actually make that feedback loop and that connection between either methods that we develop and experiment in teaching and in the labs, and then moving that into design projects.
Yeah, I mean, there's a reciprocity between the work that we do in the research labs versus the one that we do in HANA. In terms of manpower, it takes crews or a number of students or a number of people to build something like the Ashen Cabin, and so we did it over multiple years. First focusing on the concrete, then focusing on the wood. And it's usually, we do it in a concentrated effort over the summer with maybe a team of, let's say, 6 to 10 students who work with us during the whole summer. And that's how we built these projects. Now, that's currently the structure that we're working with, but in the office, we're also now working on other projects that scale things up, where obviously this is not a viable method anymore. So I think this works up to a cabin, okay, but beyond that, it's not a suitable system.
Well, beyond that is engaging with building industry and both, let's say, advanced building industries such as 3D printing systems, but also conventional contractors. And so this is what we're kind of working on right now.
Thanks. Thank you so much. Other questions?
Another question? Just raise your hand and I pass the mic.
They're a bit shy here. The gravel. Why gravel?
So huge.
Why gravel, not sand?
It's a good question. We didn't try the sand. I guess the sand would pack it more densely and would flow a bit more easily. Would probably also weigh more because the gravel has a little bit of, I guess, holes in it. And we do quite like the sort of gravelly interior. I mean, there are these kind of brutalist notions that we're working with from a material point of view when it comes to the concrete. You know, both the sort of texturation of it, but also the interior graveliness of it. And we like these references as well. And we were quite content with the gravel after we tried it at first, and then we just stuck with it.
It looks great. I wish it was on the outside as well. That was the.
Yeah.
then that would make no sense, printing the thing into a gravel, you know. Or maybe it would. You could reverse.
Yeah.
You could. Yeah, maybe not. What's it? Anyway, whatever. There's a word for when you pile stuff up like sand and gravel. The angle it wants to.
Yeah, the angle of repose.
Repose. That's it. The angle of repose. Yeah. So we have another question. A better question than mine. Here we go.
Hi, maybe not such a technical question, but actually one about kind of ornamentation. You mentioned maybe in the load-bearing column that the sort of the topological or structural optimization you went through ended up kind of making a sort of beautiful column in its own way. For you, where does sort of material experimentation and the technical side of realizing that drift into kind of architectural play and ornamentation? Because clearly there is, you know, a more playful side to also machining those boards in the fashion that you did, or, you know, designing that column in the way where it sort of became, you know, spandreled, if you like.
Well, that's a really, that's a really fantastic question. Thank you. I think the word play is really important for us. Concrete is not the most pleasant material to work with. If you all have kind of lifted how concrete heavy is, and one needs to find, amusement in the design process and working with the material. I think the ornamental aspect comes in where I would say our design process and our way of making is not always determined by optimization. We acknowledge it has the capacity to be optimized, and we can optimize the sort of structural form or to make it efficient. I think for us, our end goal is not to make the most efficient building, but rather how we can develop certain architectural language or develop certain tectonic characteristics. So it works with multiple narratives, but optimization is not what is the final decision maker in the process. And sometimes that comes back to the sort of more top-down decision. We as designer, our, let's say, personal obsessions, where it comes into play, that's where we prioritize some of our decision-making process, I would say.
Thanks.
Yeah, the chat is on screen, Pete. Sorry. Thank you. So, well, I mean, I totally agree. I think this thing about, you talked about the dance between machine and human activity is really nice. It's like, it probably is an accidental thing as you're making the projects, but actually the sort of qualities of something being constructed is just not discussed most of the time. I think it was the only person, probably one of the few people that ever talked about it was Cedric Price. He gave probably his last lecture here, and but he gave a technical lecture, and he talked about the qualities of. We talked about designing something and imagining who's got to, the poor people that got to construct it, and thinking ahead in a way, and that being an interesting, a not horrible process, and in fact in some ways enjoyable, and so that's a sort of not an inconsequential observation in a way. I just think that idea of the dance between the machine and human thing is really nice, and in a way that's, you can sort of think that's, you're not going to get rid of one or the other, because or why, you don't need to necessarily, but you employ the human activity where and when you need it in an interesting way. So I really like that. So thank you so much. So are there any other thoughts, questions, validations? They look very happy. So thanks again. That was terrific. Thanks for joining us online. That's brilliant. Thank you.
Thank you very much.
Thank you. Thank you for the questions that we've been facing.
And when you're in Europe next time, tell us and we'll get you in. Okay.
Yes, sounds great. Thank you.
Yeah. Okay.
Have a good evening.
Bye.
Bye-bye.
Bye-bye.
Bye.